Assalamualaikum warahmatullahi wabarakatuh. I respect Ma'am Daisy as the examiner. Thank you for the opportunity given to our group, which consists of me, Alifiah, and RP30, and Salsa and RP9. On this occasion, we will present the final project that we have compiled. The title of our final project is Effective Fineness of Crab Cell, CHITOSAN, and FERRIC chloride as coagulant in laundry waste treatment. Along with the increase in population in Indonesia, the amount of waste generated also increased. The waste is the rest of the activities which, if not treated, can cause environmental pollution. In example is the pollution that occurs in rivers in Surabaya, based on East Java Governor Regulation Number 61 of 2010 concerning the determination of water class in river water Surabaya. River water starting from the Lirip floodgates to Jagir is designated as second class. This second class water quality is intended for water recreation, infrastructure or facilities, freshwater, fish cultivation, animal husbandry, water for irrigating agriculture, and for other use that require the same water quality as that use. This result in river water in Surabaya can no longer be reserved for drinking water, raw water as required by the first class water quality. Based on the result of preliminary testing on laundry waste from one of the laundry business providers in the Bula area, Surabaya, it shows that COD levels are 712 milligrams, TSS is 192 milligrams, BOD is 19 milligrams, detergent is 19 milligrams, and phosphate is 5 milligrams, and oil and fat is 16 milligrams. If view from the East Java Governor's Regulation Number 72 of 2013 on wastewater quality standard for laundry business and or activities, some levels that are still above the quality standard include COD, TSS, and BOD anionic surfactants parameters as well as oils and fats. The maximum levels for COD are 250 milligrams, TSS is 100 milligrams, BOD is 100 milligrams, detergent is 10 milligrams, phosphate is 5 milligrams, and oils and fats are 10 milligrams. The high levels of BOD and COD are caused by the high organic load contained in laundry waste. In addition, high levels of detergent in the form of anionic surfactants can form from that covers the surface of water bodies. These two things cause a decrease in the dissolved oxygen content in the water body. Even the coagulation flocculation process can be used as an alternative in improving the quality of the laundry liquid waste. Ferric chloride is one of the most widely used chemical coagulants besides polyaluminum chloride and alum. Ferric chloride is able to bind organic materials quickly and from strong flux that can accelerate the disposition process. In addition to chemical coagulants such as ferric chloride, there are also natural coagulants or biocoagulants. The existence of this biocoagulant is based on increasing human awareness regarding the dangers posed by the chemical coagulant. Waste from crustacean cells can be alternative for the manufacture of biocoagulants because it contains chitosan, which is a derivative of chitin. This waste is degraded in a very long time, and in some countries cause problems with limited land. Crab cell has a chitin content of 71%, while shrimps has a chitin content of 20 to 30%. Formulation of the problem. Number 1. What are the conditions of temperature and contact time for the optimum distillation of the value of the degree of distillation in crab cell chitosan? Number 2. What are the results of the analysis of the quality standard of crab cell chitosan on the parameters of water content as fat, protein and the degree of distillation. Number 3. What is the condition of the optimum dose of CHITOSAN and FERRIC chloride as a single coagulant to decrease the levels of COD, BOD, and anionic surfactants? Number 4. What is the condition of the optimum dose of CHITOSAN with a fixed dose of 1000 ppm of ferric chloride to decrease the levels of COD, BOD, and anionic surfactants?
Action taken. The action taken by the author from the existing problem is to conduct research with the CHLORIDE method to test the effectiveness of crab cell, CHITOSAN, and ferric chloride as coagulant in laundry wash treatment.
Existing problems, the author conduct research of the following steps. Number 1. Identifying the problems. Number 2. Formulating the problems and setting goals. Number 3. Conducting a field study. Number 4. Literature study. Number 5. Collecting data includes primary and secondary data. Number 6. Determine the place and time of research. Number 7. Determine the research variable. Number 8. Carry out a research.
10. Prepare tools and materials. Tools: measuring cup, beaker, Erlenmeyer, measuring flask, pipette, volume pipette, funnel, hot plate, and magnetic stirrer. 0.25 mm sieve, oven, desiccator, filter paper, thermometer, pH indicator, and analytical balance, a set of gel test tools, testing instrument for COD and BOD5, and anionic surfactants. MBAS, FTIR, testing instruments, and testing instruments for water, as fat and protein content. Ingredients: crab cell HCl 37%, NaOH 60%, NaOH 5%, acetone, pure reagent, ethanol 70%, CH3COOS 1%, I2KI, H2SO4, AgNO3, aqueous, ferric chloride, laundry wash. 11. Making CHITOSAN from crab cells. Crab cell wash from a seafood restaurant in Surabaya is boiled and then washed with water to remove dirt. Then dried in the oven at a temperature of 110 until 120 degrees Celsius for 1 hour. After drying, it was crushed and shaved with a 0.25 mm sieve to obtain a powder with a particle size smaller than 0.25 mm. The sieve results are used as samples. 12. Carry out demineralization stage. A total of 1943 grams of crab cell powder was added with 29,000 mm of 1.5 molar HCl with a ratio of 1 divided by 15 with between the samples and the solvent. The mixture is heated at 70 until 80 degrees Celsius for 4 hours while stirring at 50 rpm and then filtered. The solid obtained was washed with distilled water to remove the remaining HCl. The filtered obtained was tested with AgNO3 solution if no white precipitate was formed. The remaining Cl ions had disappeared. The solid were dried in an oven at 70 degrees Celsius for 6 hours to obtain crab cell powder without minerals and then cooled in a desiccator. 13. Perform deprotonation stage. 3.5% NaOH solution was added in a ratio of 1 divided by 10 between 350 grams of the sample from the demineralization stage and 3,500 mm of 3.5% NaOH. The mixture is heated at a temperature of 65 until 70 degrees Celsius for 4 hours while stirring at 50 rpm. The solid was filtered and cooled to obtain chitin, then washed with distilled water until the pH was neutral. The obtained filter is treated with purate reagent. If the filter turns blue, it means that the protein has been lost. Cytine that has been washed is added with 70% ethanol to dissolve 100 mm if dissolved CHITOSAN and then filtered. Washed again with acetone and hot distilled water to remove color is 100 mm, dried at 80 degrees Celsius for 6 hours and then cooled in a desiccator. 14. Perform deacetylation stage. Cytine is deacetylated by adding concentrate NaOH with a concentration of 60% with a ratio of 1 divided by 20 between cytine and solvent. The mixture was stirred and heated at several temperature variations, namely 120, 125, 130 degrees Celsius for several variations of time, namely 4 hours, 5 hours, 6 hours, each using 5 grams of sample dissolved in a 100 milliliter of 60% NaOH. The solution is separated and filtered through filter paper. The solid was dried at 80 degrees Celsius for 6 hours, then the CHITOSAN was baked. Perform FTIR test to determine the value of the degree of deacetylation in 1 gram of the resulting sample for each variation of temperature and contact time. CHITOSAN as much as 25 grams with the highest degree of deacetylation will be tested for water, as fat and protein content to be compared with the quality standard of CHITOSAN. 10 grams of CHITOSAN was dissolved in 1000 mm 1% acetic acid solution with a ratio of 1 divided by 100 between CHITOSAN and solvent to be used as coagulant. 15. Analyze the degree of deacetylation done after crepe cell CHITOSAN was added 60% NaOH through the deacetylation stage with several variations of contact time 4 hours, 5 hours, and 6 hours, and temperature variation 120, 125, 130 degrees Celsius. The value of the highest degree of deacetylation will be analyzed for moisture as fat and protein content. 16. Analyze water as fat and protein content. Carried out for comparison with existing CHITOSAN quality standards. If the value is close to or equal to the quality standard of CHITOSAN, it can be said that crepe cell CHITOSAN is of good quality. The reference is analysis of the association. 17. Perform a jar test coagulant method to compare several doses that may show different processing results. Prepare a set of jar test tools with for 1000 mm beakers. Samples of wastewater whose pH has been measured initially are put into 4 beakers as much as 1000 mm. In experiment 1, crepe cell CHITOSAN coagulant was added with doses of 100 ppm, 150 ppm, 200 ppm, and 250 ppm while stirring rapidly at 150 rpm for 2 minutes, stirring slowly at 60 rpm for 15 minutes, and allow it to settle for 30 minutes. In experiment 2, added ferric chloride with doses of 100 ppm, 150 ppm, 200 ppm, and 250 ppm. In experiment 3, crepe cell CHITOSAN coagulant was added with doses of 20 ppm, 40 ppm, 60 ppm, and 80 ppm. 18. The filter from the jar test was analyzed for level of COD, POD5, and anionic surfactant MBAS to determine the effectiveness of several types of coagulant in reducing pollutant levels in laundry waste. 19. Analyze pollutant parameter before and after coagulant to determine the decrease in pollutant load concentration. After going through the step above, the results obtained are 1. Deacetylation degrees analysis. By using FTIR spectra, the DD values in 9 samples of each cell CHITOSAN were in the range of 62.4% until 76.1%. This shows that all samples of CHITOSAN have met the DD standard, which is greater than 60%. The highest DD value was found at a temperature of 1025 degrees Celsius and a contact time of 6 hours at 76.1% samples of capsule CHITOSAN with the highest GD value were used for comparative analysis with quality standard and as a coagulant to compare with ferric chloride in laundry waste treatment. 2. Analysis of moisture as fat and protein content. To determine the quality of CHITOSAN, approximate analysis was carried out in the form of moisture as fat and protein content and then compared with the applicable quality standard. The fat content did not meet the quality standard, while the water, ash, and protein content had met the quality standard. The value of fat content is 0.68%. The size of the value of fat content is due to the reduction of minerals and oxide due to the demineralization process. The value of water content is 6.35%. The value is influenced by the process and duration of drying. The amount of CHITOSAN being dried, the surface area of the CHITOSAN, and the storage condition of the CHITOSAN. The amount of minerals contained in CHITOSAN can be seen from the ash content. The demineralization state is able to minimize the ash content to 2.54%, has met quality standard. Protein content of 1.73% meets quality standard. The lower the protein content, the better the quality of CHITOSAN because at the stage of making CHITOSAN, there is a deproteination stage to remove the protein content. 3. Analysis of decrease in COD, POD5, and MBAS levels with single coagulant. COD of CHITOSAN. The removal of COD level with CHITOSAN coagulant increased with increasing dose from 100 ppm, 150 ppm, and 200 ppm, namely 46.61%, 62.98%, and 63.94%. This shows that the more CHITOSAN added, the lower the COD level. At a dose of 250 ppm, the efficiency decreased to 42.18% because of the excess positive charge of the CHITOSAN coagulant, so that the colloid binding became less than optimal. The optimum dose of CHITOSAN is 200 ppm because at that dose it undergoes colloid stabilization, namely the process of stabilizing the colloid, which is contrary to nature of the coagulant process where colloids should undergo a destabilization process. COD ferric chloride. The removal of COD level with ferric chloride coagulant increased with increasing dose from 100 ppm, 150 ppm, 200 ppm, and 250 ppm, namely 60.67%, 68.37%, 73.96%, and 79.93%. It is not known that excessive amount of coagulant can cause colloid efficiency of removing COD level with increasing dose. The optimum dose is 250 ppm with a removal efficiency of 79.93%. POD5 CHITOSAN. The removal of POD5 levels with CHITOSAN coagulant increased with increasing dose from 100 ppm, 150 ppm, and 200 ppm, namely 50.76%, 53.97%, and 56.43%. However, at a dose of 250 ppm, it decreased to 41.04%. POD5 ferric chloride. The removal of POD5 levels with ferric chloride coagulant increased with increasing dose from 100 ppm, 150 ppm, 200 ppm, and 250 ppm, namely 49.54%, 53.5%, 61.36%, and 64.17%. MBAS CHITOSAN. Removal of MBAS level with CHITOSAN coagulant increased along with increasing dose from 100 ppm, 150 ppm, and 200 ppm, namely 53.79%, 62.3%, and 76.98%. However, at a dose of 250 ppm, it decreased to 60.01%. MBAS ferric chloride. The removal of MBAS level with ferric chloride coagulant increased with increasing dose from 100 ppm, 150 ppm, 200 ppm, and 250 ppm, namely 52.26%, 53.38%, 58.43%, and 64.24%. The ability of CHITOSAN coagulant in reducing COD and BOD5 pollutant level is still below that of FERRIC chlorine coagulant because the removal efficiency value of several doses is below the efficiency value of FERRIC chloride coagulant removal. However, CHITOSAN coagulant was superior in reducing MBAS level removal efficiency up to 76.98% at a dose of 200 ppm. 4. Analysis of decrease in COD, BOD5, and MBAS level with a combination coagulant. The allowance for COD, BOD5, and MBAS level increased along with the increase in the dose of CHITOSAN coagulant. 20 and 40 ppm, namely 68.45%, 71.55.63%, 66.42%. This shows that the more dose of CHITOSAN coagulant added, the lower the level of COD, BOD5, and MBAS ferric chloride as a single coagulant when compared with when it was the main coagulant sold and increased in the value of removal efficiency at the level of COD, BOD5, and MBAS, which were initially at a dose of 100 ppm of 60.67%. Therefore, the coagulant process with this combination coagulant can be used to optimize the removal efficiency. However, at dose of 60 ppm and 80 ppm CHITOSAN coagulant decreased the efficiency of removal of COD, BOD5, and MBAS level by 60.01%. 52.43%, 77.47%, 57.50%, and 43.75%, 32.45%. This was due to an excessive dose of CHITOSAN coagulant, which was added while 100 ppm of ferric chloride as the main coagulant had been added. From this result, it can be concluded that 1. The optimum temperature and contact time for the acetylation in the analysis of the degree of the acetylation DD of capsule CHITOSAN were 125 degrees Celsius and 6 hours with a DD value of 76.1%. 2. The result of the proximate analysis on capsule CHITOSAN showed that the fat content 0.68% did not meet the quality standard, while the water, ash, and protein content had met the 3. The optimum dose of CHITOSAN as single coagulant is 200 ppm with COD removal efficiency of 63.94%, BOD5 of 56.43%, MBAS of 76.98%, while the optimum dose of ferric chloride as single coagulant is 250 ppm with COD removal efficiency of 79.93%, BOD5 of 64.17%, and MBAS of 64.24%. And the last, 4. The optimum dose of CHITOSAN added with a fixed dose of 100 ppm ferric chloride is 40 ppm with COD removal efficiency of 71.67%, BOD5 of 81.14%, and MBAS of 66.42%. That's our presentation. Thank you for your attention. I'm Aulia Salsabila and my colleague Alifiah Revita saying goodbye and wassalamualaikum warahmatullahi wabarakatuh.